Concentrated sulfuric acid will generate sulfur trioxide in the reaction mixture in the same way as that of nitric acid. And that is what I had asked you people to write. I don't think there is any point in asking whether you have written or not. That doesn't make any sense at all. By the way, anybody else tried that with their hand? One second, let me see, somebody is coming. Okay, see what. One second. Anybody is written? Anybody who has written how sulfuric acid is getting generated, sulfur trioxide is getting generated from 2 molecules of sulfuric acid? Anybody? Any one of you have written it? Anybody who has, you can, if you have done it, you can just say yes, unmuting your speaker or mic. Yeah. Nobody? Okay. So there is no point in asking that. We will just go to the mechanism, how sulfur trioxide is generated, which I have already written. I'll just wipe out this stuff. Maybe I will. I think it's better I take a page further. Let me take it out. One second. Let me raise this, take it up. Yeah, things are there which I have already prepared the slides and uploaded. Video and uploaded. So that is what I have done. So we are actually repeating that whatever I have uploaded. Anyway, let's see. See here, we have sulfuric acid, S double bond O, OH. In the same way as this will, I think we not done this yesterday. Am I right? Did we do it? Yes or no? If I have done it, please, I don't want to waste time. Okay, I think I have not done it. I have asked you people to do it. So I will just draw this. Now, see here. Now, I told you in the case of nitration, one molecule of sulfuric acid is acting as an acid. Acting as an acid means proton donor. Proton donation means this movement of electron. Look carefully here. This is what is meant by proton donor. This is acting as an acid, and this sulfuric acid, see, remember that this sulfuric acid is acting as a base. This sulfuric acid molecule is acting as a base. Okay, don't tell anybody that I have told sulfuric acid is a base. So I'll put it in inverted form. In this particular reaction, one molecule of sulfuric acid is acting as a base. It is abstracting the proton from the other sulfuric acid. So I have to write the arrow. I have to write the arrow in the opposite side, moving each pair of electron to the oxygen. So what I get is SO3. Who has come just now? Now, how many members are in the group? I don't know what's the total number. Anyway, you can add anybody. I don't mind if somebody is interested. Okay. Now it's SO3, HSO4 minus. See here. This is what you are getting here on this side. This is HSO4 minus. That is what I have written here. Plus, see that HO, one H here, And then you have sulfur, everything remains the same, SO2SO, you have the second OH group, and then double bonded oxygen. And remember, you have to put a positive charge here because this has donated a lone pair of electrons. Now what happens next is, see this is the driving force of this reaction. It goes off and gives you sulfur dioxide. See that? It takes away, takes your H2O out plus SO3, SO3 plus what? H plus, this H plus is taken by this HSO3 minus. See that? So sulfuric acid is acting only as a catalyst. One molecule of sulfuric acid is acting only as a catalyst. But remember, one molecule is consumed. Okay, so this is how the sulfur trioxide, a neutral electrophile, is generated during a sulfonation reaction. This is what is called a sulfonation reaction. Sulfonation. Now, so that is sulfonation. So that completes, I think we have talked much about your electrophiles. Okay, now what we have to deal with is nucleophiles. I don't know what nucleophiles I have written. Let me check it up. I have already written that. I will, I think, yeah. Okay. Did we mention this Fourier curve calculation reaction, acylation reaction? Yes or no? Can anybody tell me? Did I mention formation of a helium ion?
No.
No, yeah, I not mentioned. Okay, this is formation. Yeah, so that also I will mention. Electrophile is this is in the formation in the Fourier reactions. In Fourier reactions, there are two types of Fourier reaction. One is alkylation, the other one is acylation. Okay, in acylation, as COCH3 group is generated, COCH3CO, and that is what is called acyl group. Now let me see how we can make it. Here, see here, the reaction, the electrophile is a helium ion, CH3, C double bond O, with a positive charge here. And this can even have a resonance structure. This molecule, this lone pair of electron contributing to this. See here, it is getting stabilized. So the positive charge can be delocalized over the carbon and the oxygen. See here, oxygen with 3 bonds that we have written yesterday. It is allowed. You can have oxygen with 3 bonds, but it will carry a positive charge. Okay, right. Now, so this is now how is this getting formed? What is the source of this electrophile? The source is RCOCl. I'll put CH3 itself. You can replace this with RCH3COCl, acid chloride. And acid chloride is generated from carboxylic acid. Acid chlorides are generated from carboxylic acid, which I have shown here. Okay. So let me just show you that part. Yeah. See, this is carboxylic acid. This can be converted into acid chloride by reaction with SOCl2. You can note down, any carboxylic acid can be converted into the acid chloride by reaction of the acid with SOCl2. SOCl2 is known as thionyl chloride. Thionyl chloride. Thionyl chloride. So COOH is converted to RCOCl. Now see why you are converting this. That is because the OH here, if you can break this, it is okay, good. That will make a helium ion. But it is not easy to remove the OH group from the molecule. It is not easy to remove the OH group. Okay, so you are converting the OH group into a group which is more, which is a better living group. Now, why is Cl a better living group than OH? See here, this is Cl, this is OH, this is OH. A better living group means easy to break this bond. Easy to break this bond. This is what is called better living group. So that the Cl goes as Cl minus. OH goes as OH minus. Okay. So this is by inductive effect. The chlorine is more electron attracting than oxygen. And therefore this bond is very weak. Very, very weak. So it can be very easily broken. Unlike your oxygen OH bond. That is why Cl is a better liquid group, and therefore carboxylic acid is converted into carboxylic acid is converted to acid chloride. Now once the acid chloride is formed, look here. This is the acid chloride. That is reacting with AlCl3. That also we have seen in the case of alkylation or utilization. Okay. Or this way. RCOCl, this gives, it forms a bond with aluminum chloride, AlCl. Okay, it forms a tetravalent aluminum ion. Okay, so what you get is from here you get R C double bond plus, and what's the counter ion? AlCl4 minus. AlCl4 minus, and see the minus charge is on the aluminum atom. We have already mentioned about octet role. Aluminum is Lewis acid. It is does not have an octet, and therefore it can accept electrons. Okay, so that is what is happening here. It is forming the helium ion by breaking of this bond. See, what's it looking? Yes. So it is this helium RCO, which is called helium ion. You can see that. See now, here, no lone pair here. Yeah, there is no lone pair here also. So this it's carrying a positive charge. It's carrying a positive charge on the carbon, and this can be resonated, and this is what is a helium ion. So these are the different methods by which you can generate a helium ions, electrophiles. Now let's look at what are nucleophiles. Nucleophiles are also reagents which you have to use uh, in chemical reactions. Okay, now definition wise, oh, what is that? Okay, definition wise, it is electron rich species due to the presence of lone pair of electrons. Okay, they are electron nucleophiles are electron rich species due to the presence of lone pair of electrons, or maybe because of the pi bond. There are certain compounds which are containing pi bond. Say, for example, an alkene. This can act as a nucleophile. Why? It is not a pi bond. These electrons can be shared with it. Pi bonds are weaker than sigma bonds. So even pi bonds are also nucleophilic. Now the examples of nucleophiles: OH minus, Cn minus, I minus. Remember, I minus is supposed to be the strongest nucleophile. I minus is the strongest nucleophile. Okay, you can find the reason. You can definitely get the reason why I minus is a good nucleophile. Because nucleophile means it should have electrons to donate. It should have electrons to donate. That is the meaning of nucleophile. It should be, that is, nucleophile should be ready to donate electrons. Okay. And these electrons should be available in the valency shell. Okay. And they should be ready to be shared. Now see here, you have the I minus and compare that with the fluorine minus. Both I minus as well as fluorine are having 7 electrons in the outermost orbital. But iodine has got so many shells in between, and therefore the inner nucleus will not get an effective control on the outermost orbital. And therefore, these electrons in the outermost orbital are fairly, what should I say, have less control, are less controlled by nucleus and can be easily kicked out. The outermost electrons in a reaction can be easily kicked off in the case of iodine. But in the case of fluorine, they are very closely held to the nucleus and strong attraction from the nucleus into it. So I minus is a better nucleophile. So the nucleophilic capacity is I minus, Br minus, Cl minus, then comes your OH minus. Okay, so these are nucleophiles. Now let's look at reaction intermediates. Anything else to be now see here? We can think of reactions between electrophiles and nucleophiles. Okay, just see the reaction. Let me wipe this out. CH3. Yeah. See this? We have H plus that reacts with a hydride ion. H plus reacts with a hydride ion. What is hydride ion? Look here. Hydrogen with a pair of electron and a negative charge. This is hydride ion. Now, hydride ion is formed from NaH, sodium hydride. NaH is sodium hydride. You can generate the hydride ion from NaH. Suppose you are reacting this with an H plus. What product you get? A hydride ion is reacting with H plus. What product you get? That's one thing. Why don't you look at this on this side? H plus is reacting with OH minus. From where will you get OH minus? Okay, where will you get OH minus? OH minus can be generated from sodium hydroxide. That is what I have told you. And H plus can be generated from acid. So H plus plus OH minus should give you H2O. H plus can be generated from. So you get H2O as the product. You get H2O as the product. What will you get if you are reacting a CH3 plus with a CH3 minus? What will you get if you are reacting a CH3 plus, that is a carbocation with a carbanion, methyl carbanion? What will you get? Yeah, you can write a Arrow-Cushing mechanism for this reaction. Where is my cursor? Yeah, see here. You can write an Arrow-Cushing mechanism, nothing to do because you are accepting electrophile of electrons, and your product is an ethane molecule, CH3. Product is an alkane. Oh, how come there are two bonds? Let me. It is CH3 okay. Oh, CH3 I should write. There is a D here. I should remove that D from there. So CH3. Okay. Now let us look at this one. A CH3 plus is reacting with NH3 molecule. CH3 plus is reacting with NH3 molecule. Now can you identify which is electrophile, which is nucleophile? Just try in a paper. Yeah. Which is electrophile, which is nucleophile in this case? Which is the one? This is electrophile. And this is nucleophile. Simply by looking at the structure, you should be able to remember that. You can look by heart of this. Okay, so this is so these are the electrophiles and nucleophiles. You can identify each electrophile in each nucleophile in any particular reaction. Now let us look at what is carbocations, carbanions, and free radicals. Okay, so before I think the time will be up within no time. Please do one thing. All of you try to come a little earlier, like 10 minutes to 11. I will try my best, so that you can, those who are interested can really log in a little faster. Don't forget that. So we will just take up what are carbocations, carbanions, and free radicals. Okay. Now, carbocations are electron species which are positively charged. Species which are positively charged, they are called carbocations. Examples of carbocations, see here, C3 plus, this one, this is also carbocation. And here you have isopropyl carbocation, and tertiary butyl carbocation. Tertiary butyl carbocation, all of them are positively charged. So carbocations are positively charged species. The charge is on the carbon, you remember. So the charge is on the carbon. And what about Geometry of carbocation. What is the geometry? What is the hybridization? If we ask you, please at least write something. Write on the board. What is the hybridization of the carbocation? See, carbocation is having a positive charge. That means it is having an unhybridized p orbital. So this information gives you something about the hybridization. Okay, see here, and shape of the molecule. See, you have C plus. That means you have 3 more bonds here. 3 more bonds. 1 H and 2 H. Now you have an empty orbital carrying a positive charge. So this is your carbocation. And this is trigonal planar. It is trigonal planar. Trigonal planar means it is trigonal planar. That means if you rotate this along this axis 90 degree, all these hydrogens will come to the plane. See here, all the 3 hydrogens will come to the plane. And now the p orbital will be perpendicular. Okay, if you look from here, it will be perpendicular. So this is a carbocation. Okay. Now we have different types of carbocations. A methyl carbocation with 3 hydrogens, and then ethyl with 1 more carbon, which is a primary carbon, and then if it is connected to 2 CH3 groups, it's called a secondary carbocation, and if it is connected to 3, it is called a tertiary carbocation. Okay, see here, this is primary, ethyl, see here. Okay, so this is primary, this is ethyl. Ethyl is also primary. Please remember, this is methyl. Methyl is having only 1 carbon. So we treat methyl separately. So this is ethyl, and this one is isopropyl. This third one is isopropyl, and this is tertiary butyl. See here, you have CH3, CH3, and CH3. This is tertiary butyl. Okay, so the order of stability of these carbocations, tertiary butyl is the most stable one. Tertiary butyl carbocation is the most stable one, then secondary, then primary, and then methyl. So that is the order of stability of the carbocations. So geometry we have discussed. The geometry is there. Geometry we have discussed. It is trigonal planar. The hybridization is sp2. sp2 hybridization. So stability. Now, formation of carbocations. How can you form the carbocation? That is by heterolytic bond fission, you can form a carbocation. By a heterolytic bond fission, you can form a carbocation. Now, what is the type of heterolytic bond fission? Let me see whether I have written something here. Yeah. Now see, here, formation of carbocation. CH3Cl, electrolytic bond fission. Electrolytic bond fission, it forms CH3 plus. Okay, but remember this is not very easy because you can